Are you thinking?
All right, here we go. So, let me get your attention here. So I want to go through something today that you guys, this is not a big deal. We're going to do an introduction to polynomials.
Oh, yeah.
You guys have, I don't know if you've ever heard the word polynomial or not.
Yeah.
You have heard the word polynomial?
I think so. Don't have any idea where.
Okay, but so you may have some vague recollection. That's all right.
Big from you.
You'll understand, and probably maybe from me. I don't know if we've ever really talked about. I don't think there's any of you guys would have ever talked about this in detail in the past. So you've already dealt with polynomials without knowing it. Like for example, in our exploration of quadratics, which continues, we've talked about trinomials quite a bit. We've talked about quadratic trinomials, things like this. Like for example, 7x squared minus 3x plus 4, right? We talked about trying to factor quadratic trinomials. We've talked about writing quadratic equations in standard form, which means we write them as a trinomial. Here's another example. Okay, what do you notice? Well, what about binomials? Talk about binomials also. Binomials have been things like when we've done binomial expansions. I don't know how much we've used that word either. Maybe I've slipped it in there a little bit, but binomial would be something like 2x plus 4 or 3x squared minus 9 or something like that. And we've even talked about monomials very briefly. I've said the word, and I've said the word in this context. We've talked about factoring out a greatest common factor, which we've also called a monomial factor. So sometimes we're able to do something like this, for example. We can do something like, if we started off with 3x squared plus 15x, we were able to write that as 3x times the quantity x plus 5, right? And in that case, that's a monomial. Okay? So what does tri mean?
3,
What does bi mean?
2,
What does mono mean?
4.
Okay, so given, no, not 4. So given that information, what do you suppose a trinomial is?
3.
3 whats?
Sides.
No. 3
3 whats? What do we have 3 of?
Are 3 variables,
things you
Well,
don't know.
because you have x squared, x.
Like x's.
You're right, I have different, I mean, but they're both x's, aren't they? What's different about them though?
One
I
squared.
can't add those up because they're not what?
The same.
3 like different bases or 3?
Different bases, but I can't add up 7x squared and negative 3x because they're not like terms, right?
Yeah, that's what
So these are, terms are things that are being added or subtracted, right? So a trinomial is a sum of 3 different terms that don't combine, right? That are not like terms. A binomial is a sum of 2 unlike terms, and a monomial is just a single term, but there's more to it than that, right? There's a little more to it. So what does poly mean? Many. So polynomial just means
Shout out to
many
Mrs.
terms, right? But you can't just have any kinds of terms. There are some specific rules we have to follow if this is going to be a polynomial. And these are all examples of polynomials. What do you notice about the exponents? The powers of x. It doesn't have to be x. It could be y's, but usually it's x's. That's an x squared. That's an x to the first power. So there's an invisible 1 there. And what's that?
There's no
4 is the
x.
coefficient of x to what power?
No.
You're right.
0.
So what would that be?
0. X is
Yeah, x to the 0 is equal to
0.
no
1.
1. So it's just 4 times 1, right? It follows the pattern of second power, first power, 0th power, but we just don't write it. Okay? But it's there. But if you look at all these terms up here, what do you notice about the exponents? Are there any negative exponents?
No.
No. Are there any fractional exponents?
No.
No. Are there any irrational exponents? Square roots or no. The exponents are all whole numbers, aren't they? Right? So polynomials it's just a sum of terms, but the recipe for building each term there's two things. The exponent is a whole number. And now these are sort of specific examples, and so we haven't really talked about coefficients being anything other than integers, right, in the polynomials we've dealt with. Notice that these coefficients are all positive or negative whole numbers, so they're integers. They could be other things too. They could be things like fractions or decimals, or they could even be irrational numbers like square roots or pi or something, right? The only thing that the coefficients can't be, and you guys know what I mean when I say coefficients, right? Coefficient, what are they? Ken? The number in front of x. So what are the coefficients? If we look at -2, 1, and
11.
negative 11,
11.
right? Because that's actually times x to the 0.
Yep.
Okay. So the coefficients just are real numbers. The only thing they can't have is an I in them. Okay, so these are just real.
We can't.
So the coefficients are real, meaning no imaginary numbers. That's it though. Okay. That's our recipe for a polynomial. Okay, so let's look at a couple quick examples. This is just something from the homework, and you'll see this isn't, this stuff isn't hard. Oops. Okay, so real quick, I'd like you to, don't say anything yet, everybody look at those, and I want you to pick out the examples that are polynomials. That are polynomials. And let's just go through these
Oh, I was trying to do these
one by one and see what we get. Nathan, do you think that first one's a polynomial?
Yeah.
It looks good. Anybody see any problems with it?
Oh, the exponent's not a whole number.
Oh, okay.
Yeah.
We got one issue there, don't we? Because we've got an exponent that's a decimal. So we got to cross him out. What about the next one? It looks fishy because we got those square roots of 5, but that's okay because those are coefficients. Right, Trent?
Sure thing.
Okay, the coefficients just can't have i's, and none of them do. The exponents are all whole numbers, so that one, that's a
Works.
check. Okay, next one. Yeah, that's good. What do you think about that one? Anna, what do you think about that one?
No, because that exponent, in the radical.
Oh, okay,
Radical
yep,
exponent.
there you go. No good. We have
Oh, that's why it's.
a non-whole number exponent, so no good. How about this one?
Nope. A
Nope.
non-whole number exponent again.
How about that one?
That one's good.
Because it's, what's the thing? Coefficient is,
I thought the coefficient could be like that.
It can. Yeah, the only thing the coefficient can't have is an I. So that one's fine, right? Make sense?
Yep.
Okay. All right, next issue. So polynomials are, they're just a sum of those, a bunch of terms that follow those two rules. That's it. All right, so then if we want to define like the most general possible polynomials, here's how we would do it. I just want to show this to you once. I want you guys to get used to math notation. This is going to look a little funny, but I want you to try to wrap your brain around this. You're only going to see this one time, but I want you to see if you can get a feel for what this is all about. Okay, what's all that mean?
What are those dots?
Oh,
What are those dots? Okay, so yeah, what do you think that means?
Multiply
etc.
3 times.
It continues, right? So that'd be like the dots, that's called an ellipsis, and it would be something like this. Like, what if we did 2, 4, 6, 8?
We appreciate it.
What's that saying?
that is
All the
cool.
stuff
Yeah,
keeps going in that
it's a
pattern.
long list, but it follows that pattern, right? You get the idea?
So how are we supposed to know that pattern? The one on top.
Okay, so let's figure out what is that pattern then. We got to establish what's going on with this pattern. Okay, so let me point some things out here. Let's look at this in a little more detail here. Let me just grab that stuff. Yeah, I can't. Scoot that down.
What's the last one on A?
That's a sub 0.
Oh.
Okay, so these guys are all the exponents, aren't they? And that's a 1, right? And technically there's
0.
an x to the 0 there. And so those are
Exponents.
the exponents, right? And those are whole numbers. Okay, starting at 0 and working our way up to n. Well, what's n? I mean, we don't know, right? It could be 12, it could be 100. N is just the biggest power of x. Everybody agree? Look how this is organized, right? We've got the biggest powers of x first, and we're just stepping down all the way to 0. Okay, does that make sense?
I don't get that.
Okay, ask a question.
I don't.
Oh.
Okay.
So if it's ax and x to the 12th power,
Okay.
the next one
Would
be
be
the 11th.
would be the 11th, right? Because see, we're
And
subtracting 1 from
9,
it.
8, 7. All
So
the
we
way to
get
0.
x to the 12th, x to the 11th, et cetera, all the way down
Moses.
to x squared, x to the first, x to the 0,
You
right?
have to add them all together?
Okay, and, well, yeah, I mean, we can't combine them because they're not like terms. But remember, a polynomial just consists of a bunch of many terms, right? Many terms that can't be combined, okay? But when we put it into standard form, and that's what this is in, this is a polynomial in standard form. And standard form maybe starts to make a little more sense now. Like when we say a quadratic equation in standard form, what do we get? We get the x squared term first, then the x term, then the constant, right? So we're just following the standard form for a polynomial, aren't we? Right? Okay, so polynomial in standard form, we always organize from the biggest power first to the smallest power last, right? Those are the exponents. What do we call these things? What are all...
Sub
Okay, so those are subscripts, you're right. And so each one of these things, taken as a whole, is a coefficient. What in the world do those subscripts mean? Nothing important. All they mean is that a sub n is just the coefficient that goes with x to the n power, right? In real life for math anyway, that's going to be a number of some kind, right? We're just saying this is what the form of a polynomial in standard form looks like, just like we would say, for example, that standard form, a quadratic function in standard form would just be f of x equals ax squared plus bx plus c. What are the a, b, and c? Well, they're numbers, right? They're always going to be numbers. They're not going to be a's and b's and c's. They're going to be numbers, right? Just like in this case, you know, each one of these, a sub n minus 1, a sub n minus 2 if we kept going, all the way down to a sub 2, a sub 1, a sub 0. Those are just numbers, right? These just represent the places where those numbers go, though. Okay? Make sense? Okay? So if here's our polynomial in standard form, there are some important things we can say about this. We could say that the degree of the polynomial is n, because n is the highest power of x, highest power of the variable, in this case x, right? So when you want to know what the degree is, that's all you got to do. What's the biggest exponent? That's it, okay? The leading coefficient, or the leading term, sorry, that whole thing is the leading term. Why? Because it's the first term. It's the term with the biggest power of x. And then we would say that specifically
So the front term will always have the biggest exponent?
Biggest exponent. That's how we organize a polynomial into standard form.
Okay.
And then we would say that a sub n is what we call the leading coefficient, right? It's just the coefficient of the biggest power of x.
So the n will always be the biggest, like, one in front too?
Exactly.
All right.
Yeah, yeah. And then this last thing I'll say about this is we don't really write the x to the 0, right? So if there is a term that doesn't have a variable, meaning that the variable is to the 0th power, what do you suppose we call that? If it doesn't have a variable, it's just like a 7 or a pi. Or
0,
it's not varying, is it? Because it doesn't have a variable in it.
non-variable, coefficient, constant.
It's the constant, yeah. Okay. That's it. That's the anatomy of a polynomial. Okay, so let's look at a couple examples from Moodle. Okay, how about that? So there's a polynomial, right? First thing we want to do, let's write that in standard form. Okay, so if I'm going to write that in standard form, which term has to go first?
The biggest one.
Okay, good. So we got to do the 7x to the 5th, don't we? Right. So 7x to the 5th. What's next?
7x third,
7x to the 3rd. Okay. What's next?
2x to
So plus 2x squared
plus 4x.
plus 7. Okay, good. So what's the degree then? 5. Just biggest power of x. It's a 5th degree polynomial. Sometimes people say it's a 5th order polynomial. Means the same thing. What's the leading coefficient? 7. Boom, we got it. Okay, no biggie. Okay. All right, next step. Next step is we want to add polynomials. Now we've got these polynomials, how do we add them? And you guys already know this. We've already done some stuff like this in the past with just, we didn't call them polynomials, we probably called them expressions. But you've done this stuff. What do you do? If I'm adding, don't have to distribute. If I'm adding, it's easier.
Just add 'em.
Oh,
Add
I
what-
didn't even small.
Add like terms.
Yep.
That's it, right? Think about this. Polynomial means many terms.
Just count
If I'm
3x.
adding two or more polynomials, I'm just going to add up those many terms by adding up the like terms, right?
Yep.
I'm not even going to do an example. You guys can do that,
Yeah,
right?
it's easy.
That's no big deal. Like if I put in the right answer, let's just look at the first couple terms. Well, there's only one x cubed term, so that one stays the same. But look at the x squareds. There's a negative 5x squared plus a positive 9x squared gives you positive 4x squared, right?
Plus 2x because it's positive 5, negative 3.
Exactly. Then negative 8 and positive 6 gives you negative 2 for the constant. Okay, so subtracting, you know this also. We've never specifically said it in these terms, but we've done lots of stuff like this. What do you think you're going to do if I'm going to subtract this polynomial from this one? What do we do with imaginary numbers when or complex numbers when we subtracted them? What do we do with the negative?
Made it positive. Don't you add them?
Well, yeah, we're right, but before we can add them, subtracting and adding are the same thing, aren't they? If I say 7 minus 3, isn't that just 7 plus negative 3, right? So all I have to do here is, there's really two ways you could do this. I'm going to strongly recommend one of the two ways. You could just subtract term by term, but you're more likely to make a mistake if you do that. What I would recommend is that you just distribute the negative sign to each term and then add, right? Okay. That makes sense? So it's easy, no big deal. Now the one I do want to focus on a little bit is multiplying polynomials. That's a little bit trickier. And it's not like it's hard, but you want to be organized when you do this. Okay, so let's see, there's an example. So if we're going to multiply these two polynomials out. Okay, so let's go through this process. There's two ways to do this and be organized about it. you know the process. You can already tell me, what do I have to do if I'm gonna multiply polynomials out? What's our process? We've done this with small polynomials. Like, how would you have done this?
Oh, you would just multiply the numbers.
So what if I had 2x plus 3 times 3x minus 5? What would you do?
Just multiply, like
Okay, you could FOIL, sure.
several things.
You could FOIL. FOIL is really just another fancy way of saying what though?
Distribute.
Distribute, right? We're just gonna distribute the 2x
Looks like 2K.
over the second polynomial, and then we'll distribute the 3 over the second polynomial and just add like terms, right? So you guys already know the process. You've just done it with smaller polynomials. Same thing here, right? I'm just going to distribute each of the terms from the first one to the second one, or vice versa. It doesn't matter. You could distribute from the second to the first. It doesn't make any difference. You just want to be consistent, right? So just for the sake of consistency, let's just start with the first one. Okay, so if we do this, let's distribute the negative 4x to the, negative 4x to the fourth.
No more.
Yes.
What am I going to get? What's negative x to the fourth times negative 6x cubed? And I can break this into parts. I can look at the product of the coefficients, which is going to be the hardest part, honestly, and then the product of the variables, right? So what's negative 1 times negative 6?
But,
Positive
wait,
six.
wait.
Positive
Wait,
6.
that's 4x, so are we distributing?
Yeah, I'm distributing,
I didn't
right?
think you could do that.
Okay.
Oh, okay.
See what I'm saying? Because none of these terms are like terms. They don't add up, so we've got to just distribute. Now, what's x to the fourth times x cubed?
Negative.
X to the seventh. If we multiply like bases, what do we do? Add the exponents. So I get 6x to the seventh. Okay, now here's the part where you got to really, everybody listen to this very closely. So we're going to use a method. Do you see that if I were to make this distribution all the way through, and then I distribute that term and then that term, I'm going to get a huge long row of terms that's going to be really confusing, right? So we can organize this by vertically aligning like terms. To do that, we have to keep a column for every power of x, though, all the way from 7th down to 0, okay? So let's just make a little template here so we know that this is going to be our column for x to the 7th. You don't have to do this every time, but I just want to show you how it's organized. We're going to have a column for x to the 6th, a column for x to the 5th, x to the 4th, x cubed, x squared, x to the 1, x to the 0. And we got to maintain those columns because throughout the process of all this distribution, we're going to get lots of terms that line up in each column. Now, what happens, like notice when we do our next distribution, negative x to the fourth times positive x is what? Negative x to the fifth, right? But I don't want to put that right next to this term because I'm probably going to get some other x to the sixth when I do my other distributions. You see my point? So we want to leave space, even though we don't have one. When we distribute the first term, we skip over the x to the sixth power. It might show up later, right? So we got to leave a space and move over to the x to the fifth column. And once again, you don't have to write out, label each of these columns. You just got to make sure you're leaving space, leaving enough space for the missing columns if there are some. Okay, give me a thumbs up or thumbs down on that concept. Does that make sense? Okay. What? Question?
Oh, that's good.
Okay, so when I'm distributing here, I got 6x to the 7th. The next term I would normally expect to get would be an x to the 6th power, right? But we didn't get one because look at this polynomial. It's missing the x squared term. See what I'm saying? And so we jumped all the way from an x to the 7th term to an x to the 5th term. But I don't want to write those next to each other because eventually I might end up with some other x to the 6th terms that I've got to add up. And if I put the x to the 5th one there, it's going to get really confusing, right? Because we want to have only like terms grouped vertically. I think this will, as we go through this, it'll make more sense. What if we distribute the negative x to the 4th to the 6th? What do we get there? negative
Negative 6x.
negative 6x to the fourth. So that one goes in the x to the fourth column. Okay, now let's pick a different one. Let's pick the next term, the negative 4x cubed, and let's distribute that one. So what's negative 4x cubed times negative 6x cubed?
Positive 4x.
Everybody see that? So negative 4 times negative 6 is 24, x to the 3 plus 3. So I get a negative, or a positive 24, x to the 6. Do you see why we had to leave a space there now? Right? Because those would have lined up and they're not like terms. So negative x to, or negative 4x cubed times positive x is what? Negative 4x to the fourth. Everybody agree?
Yeah.
Negative 4x cubed times positive 6 would be negative 24x cubed, right? Now let's distribute the 6x. 6x times negative 6x cubed.
That'll be negative 6x to the 4th.
Okay, so negative 36x to the fourth, 6x times x.
It's gonna be 6x.
Okay, so I'm going to scoot over to the x squared column. 6x times 6. 36x, right? And then finally, what if we do, what's another column we can do here? I guess we'll do yellow. So if we distribute the negative 1 through that polynomial, what's it going to do if I distribute negative 1? This changes the signs. So I'm going to get a positive 6x cubed. I'm going to get a minus x. And I'm going to get a minus 6. So look how good that is then. We've just got, we're going to add up all these terms, but we can just add vertically now, right? So we end up with, well, what the sum of all of our x to the 7th terms is just 6x to the 7th. The sum of all the x to the 6th is only one of them, 24x to the 6th. We only get one of those. Here we get a bunch. So what's that going to be? I know I'm going to get an x to the 4th. Just add up the coefficients. So negative 10 and negative 36 is, okay, here I know I've got x cubes. I've got negative 24 plus 6,
18.
right? Here I've got only one x squared. And then 36x minus x. And I'm done. Okay? So there's one way to go about it. You can just make columns like that. Okay, I'm going to show you one other, I think, pretty cool way to do this. And you can sort of take your pick on this one. So you can also do this using a table. So let's make a table here. I'm just going to make a row for the stuff on the top of the table and a column for stuff on the left of the table. And then all we do, we have to do the same kind of concept. We've got to make sure that we have columns for every power of x. But I'm going to put the polynomial with the most terms, I'm going to put that on the top because it's easier to write. That's the only reason though. So up here we're going to put 5x to the 4th. And I'm going to leave, so there's my x to the 4th column. Minus x cubed. Leave a column. Minus 3x squared column. Now I'm missing an x term. So what could I put there? 0. Good. I could put plus 0x, right, to hold that column. And then now I've got a minus 4 right there. Okay? The other polynomial goes down here on the side. So I'm just going to put one term in each row. So I start off with a negative 6x cubed. And then I get a x squared plus x squared. And then I get a plus x. And then at the bottom, I just get a 0. Now I probably don't have to put the 0 at the end, but I did. So now look what happens here with this. This is pretty cool. This is a good way to organize polynomials too, multiplying polynomials. I usually just use the way we did last time, because I don't want to have to mess with the table, but you might really like the table. Okay, so if we go through to do this product, then all we do is we're just gonna multiply, we're gonna find the horizontal and vertical products. So here we're just gonna multiply 5x to the fourth times negative 6x cubed, which is what? X to the seventh, okay? So what's gonna go here?
5x to the 6.
Good, 5x to the sixth. What's gonna go there?
Positive 6x to the 6.
So, okay, so positive, right, because I'm multiplying negative 6x cubed times negative 6x cubed, so I get positive 6x to the sixth. What goes there?
Positive
18x to the
What goes there?
x to the 5th, or negative x to the 5th.
What goes there?
5x to the 5th.
What would be the 6th? Because there's a 1.
I get a 1 there, so I get x to the fourth times x to the 1 is x to the fifth. Okay? How about y? What's going to go there?
0.
0. Yep. What's going to go there? So that times that.
Well, negative 3x to the 4.
Good. That's good. Yeah. Okay. How about here? What's going to go here?
You got this.
Might it just be
Negative x to
why
what?
would it be a negative? Because that's positive. And that's
Yeah, but see, I got negative there times a positive, right?
Oh,
Is
all right.
negative. Then what's the power of x going to be? Good. Okay. How about here? Somebody, I don't care. You guys just pitch in.
10x to the
24.
4th.
24
What the?
X to the 5th.
x cubed.
That's what I
It's not
meant to say.
adding.
Remember, you're multiplying. So here you're going to get 0, right? Here you're going to get,
Negative 4x, 3x to the 3rd.
okay. And then I didn't even fill these in, but that's a 0, isn't it? And that's a 0, right? And then how about, I'm missing here, how about we'll go that color?
Negative 4, or no, yeah, negative 4, x to the square for first power.
Okay, squared, right?
Oh, I was looking at the
Here.
wrong one, yeah.
Here I'm gonna get 0,
Yep.
right?
Then this would be negative
0,
0.
right?
the next one.
And then,
Negative
what are our
4x.
colors here? What we got next? That color, I guess.
Negative 4x.
0. And then over here in the corner, we got, oh, that's that color.
Black.
Yeah. 0, right? Okay, what do you notice about this, about the organization? Where do the
It's
like
rainbow.
terms show up?
In the biblioteca.
Diagonal.
They're diagonal, yeah. I mean, technically, this is really a 0x to the fourth, right? But if it's a 0, all the ones that are 0, we can just cancel. We don't even need to, right? Those aren't going to add to anything. But if we look at the diagonals, yeah, look, there's going to be all the x to the 6th terms. And there's going to be all of the x to the 5th terms to add up, right? See how that works? So that's another kind of cool way to organize it. But you got to make sure that you leave the zeros, you leave columns for the zeros or it'll mess the table up, okay? All right, so when are we out of here?
15.
10 minutes.
15? Okay, so then I'll give you guys a chance to work on this stuff tomorrow then. One more thing I just want to show you. Oh, man, turn it on. There's a shortcut for some of these that saves you some time.
Oh, goody.
Yeah. You can tell me the others like that. Well, at least one of them. This is called a conjugate pattern. If I multiply something of the form something plus something else, call it A plus B, times A minus B, where A and B are the same things, that's called a conjugate pattern. That's just the way a conjugate pattern works. And this is always equal to the difference of the squares. Okay? So there's one pattern. That's probably the least important of the bunch. Because if you, this makes sense too, doesn't it? If I were to distribute, I would get a squared minus ab plus ab minus b squared. So the plus ab and the minus ab cancel. We call those the cross products. Okay, so there's one of them. You already know this one. The next four are just some binomial expansions. We're going to take binomials to powers. If I have a plus b squared, what does that work out to be?
A squared plus b.
A squared, good. Now I'm going to show you something here. So that plus sign goes there, right? 2ab plus b squared. Now those are both to the 1 power, right? So there's some arrows I can draw here. The fact that that's a 2 means that that's a 2. What are the sums of the exponents in each of these terms? I get 2, 1 plus 1 is 2, and 2. Right? The exponents always add up to whatever the power of the binomial is. What did we do? Well, we started, think about this pattern here. I want you to see this in terms of a pattern. If you see it in terms of a pattern, you won't forget it. If you try to memorize the whole thing, you'll forget it. But the pattern is you start with all of the exponential power weighted towards the a, and then every time we move over to the next term, the power of a drops by 1 and b goes up by 1, right? See how that works? And then the outside terms are just going to be a squared and b squared, right? The inside term, the coefficient, is the 2 that shows up there in the exponent. Notice that the first sign is always going to be the plus. It's going to be the same as what's in here. Okay, so if I write up, if we use that same kind of thinking, I know you already know this one, but what are we going to get? So I know I'm going to get the same, I'm going to get an a squared, and I'm going to get a b squared, and in the middle I'm going to get my 2 because of that, a to the 1, b to the 1, right? But notice that if that's negative, I go minus there, and then I alternate. Okay? You see the pattern? Okay, so now I want you to make an educated guess. So that one you knew, but just using the rules that I just demonstrated for you, I bet you can tell me without looking at the paper what this is going to be. So what's going to go first?
Positive.
A
Plus r squared
a cubed, good. What do you think the term clear over here is going to be, the last term?
negative.
It's going to be b cubed. Okay. So what's the next one going to be? Now this is positive, so the next one's positive, right? So what are the powers of a and b going to be here? It is. It's going to be 3 times a to the, no. Remember, a drops down by 1, b goes up by 1. So a squared b, right? We know that that's a 3 because of the 3 right there, right?
Yeah, because
Everybody get that?
1 is 1, or
Okay.
3.
Now this time we're going to need an extra term though, aren't we? We need an extra middle term because in order for a to drop all the way down to 0 and b to build all the way up to b cubed, I've got to go through 1, 2, 3 steps, not just 2, right? So we're going to add another term in the middle that's also going to be a 3 because it's a middle term. And we're going to get an a times a b squared, right? And then the last term is going to be b cubed. Now notice that this is, if I cut this thing down the middle, it's symmetrical, isn't it? Right? I get 3's here and 1's there, right? Okay, so then what's this going to be? What is a minus b cubed going to be? I'm going to get my a cubed minus 3a squared b. Now it alternates, right? So I'm going to go plus 3ab squared, but then it alternates back to a minus. If it's negative, it starts with a negative and it alternates.
How come you did social sign?
Which one? Oh, which one? Up here?
No, the second.
Because this one's plus. The plus ones are always just plus. It's the negative ones that are going to alternate. They start negative, then they alternate. Negative, positive, negative, positive. Okay? And so really, from here, we could go further with this, and the rules would change very slightly for bigger powers, but not that much. Okay? But really, if you just remember those rules, this is all we ever teach is up through, we only memorize up through the cubic binomial expansions. After that, we'll use a formula, right? And I'll show that to you later, not this year.